All right, everybody. So in today's lesson, we are going to talk about the equations of kinematics. This is something that you have seen before in grade 11, but now in grade 12, we start to talk about them in a two-dimensional sense. And we are introducing ourselves to a few more of them. So just follow along, and it should look familiar, just with a bit more of a challenge when we get to the practice problems themselves. So let's just get started. The following equations are used when the acceleration of an object is constant. This means that the object is either in free fall or a constant force is acting on that object to speed it up or to slow it down. We are not dealing with scenarios where we have an acceleration that is changing. The acceleration will always stay the same, and that makes our lives a lot easier. It makes these equations actually able to be used. Because, excuse me, if we had an acceleration that wasn't constant, these equations would not be applicable. So, equation number one. This equation is just a rearrangement of the formula A equals delta V over delta T. So this is just our straight up first formula that we learned, or one of the first formulas that we learned when we were in grade 10. Acceleration is equal to the change in velocity divided by the change in time. It can be rearranged to give you the following formula. If we take change in velocity, let's use a different color here. If we take change in velocity, we know that change in velocity is equal to the final velocity, we can go v2, minus the initial velocity. If we do that, and we plug that change of velocity into this formula, we get that the acceleration is equal to v2 minus v1 over delta t. Now, it's just a simple matter of moving some different variables around. We're going to move the delta t up here, and then we are going to get rid of the v1. Basically, our idea here is our final formula. We're going to end up making it in terms of v2. So just, if you want to try, it's a nice little practice problem for you to do to move some stuff around in algebra without actually using any numbers, any numerical values. But if you do, you'll get that V2 is equal to V1 plus A delta T. So V2 is equal to V1 plus A delta T. Just rearranging our basic formula of acceleration is equal to the change in velocity over the change in time. We use this formula, obviously, in a scenario where we have no displacement. Not that we necessarily don't have a displacement, but just that we haven't been given a displacement in the question. So this formula we use when we have not been given a displacement value in the question. And you will see it. It is our first formula on our formula sheet. Equation number two. There are several steps involved in deriving this equation, so I'll go over them. Now, I won't in a test ever ask you to derive the equation, but I think it's useful for us to be able to see where these formulas are coming from and not that they're just coming out of nowhere. So, the displacement for the following VT graph down here can be calculated by finding the area underneath the graph. We have discussed this several times, that we can use the area under a graph. We did this in grade 11 to be able to find the displacement. Remember, if we have a VT graph, we need to find a displacement. This is something that you may have learned we probably went over it again in grade 11, but you were introduced to that in grade 10. You find the area. So, the area under the graph is equal to, if I want to find total area underneath a graph, I want to find the total area, well, I need to split up these two sections into their horizontal and vertical, alignments kind of. So I'm just drawing little lines across to show that all we have here basically that we're concerned with is a rectangle and a triangle. So if we have an angled line like that with an area underneath it, we have a shape that can be split up into a basic right triangle and a rectangle. So if I just told you that the area is equal to the rectangle and the triangle added together, that will be the total area under the graph. And the total area under the graph is equal to the displacement. Then we would say that the displacement is equal to the area of the rectangle plus the area of the triangle. And now all that's left to do is just write out what the area of the rectangle and what the area of the triangle would be. Actually, a lot more straightforward than it seems. If we're ever trying to find the area of a rectangle, we just do base times height, right? And in this case, base times height is just going to be our V1 is our height. It goes from V1 here up to V2. And on time, we're going from T1 to T2. So if I'm trying to find the base times the height, well, this area right here is the change in the velocity, and this area right here is the change in time. So the base of this is going to be T1 and T2, from T1 to T2. So if I'm trying to find that distance, it's the difference between the two of them. It's T2 minus T1. But in this case, if I'm trying to find the height, it's not V2 minus V1. That would be the height up here. The height here is just V1, right? So remember, keep this in mind. I'm going to put this right here. The area here is the base times the height. And remember, the area of a triangle is 1/2 times the base times the height. So in this first scenario, we'll say delta D is equal to base times the height, which I said was the height was a V1. It was just the height times the distance between, or the displacement between T2 and T1, which is just delta T. So that's our area of the rectangle. Now our area of the triangle is 1/2 times the base times the height again. But in this case now, it changes, and we have that the height is V2 minus V1, which is delta V, and the width, or the base, is the same thing. It is still delta T. That has not changed. So there we have it. But now one thing is that we don't have this on our formula sheet. We don't have this specific formula on our formula sheet, and there's a reason for that. Now, this is a scenario. We can use this formula in certain scenarios. This would be the type of scenario where we had not been given acceleration, right? There's no acceleration in here. But it's not one that we use as often. What we can actually do to find an equation that we use more often is we can combine the equation from step 1 and equation 1. We can combine step 1 and equation 1, and we can find our next new equation that we're going to use. So remember, equation 1 from way up here is just the fancy way of writing out. Let's use purple here. It's just the fancy way of writing out acceleration is equal to the change in velocity divided by the change in time. And if I rearrange this for velocity, I get the change in velocity is equal to the acceleration multiplied by the change in time. And watch this. I take this portion right here, which is what's equal to the change in velocity, and I swap it out. Remember, we did, last time I saw you all, we did substitutions. We could substitute in that delta V with, we could substitute in a delta T. What we would end up getting if we did that was we would get 1/2 a delta T times delta T. And now what you're going to see is that if I take this and I end up plugging it into our formula, which we're going to end up writing over here, we end up getting Everything at the start is the same. Delta D is equal to V1 delta T plus 1/2 A delta T. So A and delta T times delta T is just delta T squared. And there you have it. Look at that. Boom. That exists right there. Delta D equals V1 delta T plus 1/2 A delta T squared. So we have two of our formulas. Let's move on to equation number 3. Oh, actually, I forgot one thing. This scenario is a scenario where we have no V2. So all of our formulas should end up working while missing one of the variables. That's the whole idea. Okay, this next one. This equation is a combination of the two very basic equations. First off, delta D is equal to the average velocity multiplied by the change in time. Average velocity, remember, is just initial velocity plus final velocity divided by 2. And then we're combining it with our rearranged version or rewritten version of acceleration. Acceleration is equal to V2 minus V1 over delta T. If I take these two formulas and I do some work with them, again, do not freak out if you're not really fully feeling super comfortable with doing the derivations, because that won't be a test question. I'm just showing you where these formulas come from, okay? So if I take these two, and first thing I'm going to do is I'm going to isolate them both for delta T. I'm going to isolate this one for delta T, and I'm going to isolate this one for delta T. And you can try that on your own if you want a little bit of extra practice. But if I'm isolating for delta T, I will end up with 2 delta D over V1 plus V2 is equal to delta T. And over here, I'm going to have delta T is equal to, I move it up here and I move the A down, and I end up with V2 minus V1 over A. Now here's the really interesting part. I take these two right here. I take this delta T and I take this delta T, and I realize that they are the same. They are equal. So basically what I'm doing is I'm setting this equal to this. They're the same thing. They're the exact same thing. And what I end up getting is 2 delta D over V1 plus V2 is equal to V2 minus V1 over A. And then I do something that you have learned in math before. I do a cross multiplication to bring everything up to the top. So I end up bringing up this to up here, and I end up bringing this A up here. And if I rewrite these formulas now, I should end up with 2 times A times delta D, that was from me bringing the A up there, is equal to V1 plus V2 times V2 minus V1. And that was from me bringing this one up here. So now what I can do is I can multiply these through. And I end up with V1 times V2 is V1 V2, and then minus V1 squared plus V2 squared minus V1 V2. This is a very, very similar situation to having x plus y times y minus x. And what ends up happening is the x, y's cancel, and you end up with just the squareds. So trust me, we do this. Again, I'm going somewhat quickly through this because it's just the derivation, okay? But we end up with V2 squared minus V1 squared. That is what we get when those are set equal to one another. And that's 2A delta D. So this is a perfect start. This is a fantastic start. This is exactly what we want to end up at. Kind of a weird little combination of those two. And my final step here is just to bring them up here. And what I'm going to do is I'm going to isolate for V2 squared, because I'm just looking at my formula sheet here and it's isolated for V2 squared. And if I do that, all I have to do is move that V1 to the other side, and I get V2 squared is equal to V1 squared plus 2A delta D. Now, as maybe somewhat confusing as that was, isn't that satisfying, being able to just move all this and perfectly get our new formula that we were missing? It's a derivation. Do math, continue on with math, pre-calc, calculus, and university level, et cetera, you will get very used to doing derivations. So in this scenario, we have no time. There's no time. So far we've seen a formula where we have no displacement, a formula where we have no acceleration, a formula where we have no final velocity, and a formula where we have no change in time. And that's it. That's all that we need to know. We don't necessarily need to go over a formula where we have no initial velocity. The reason for that is there's a few reasons. One of the main reasons being that any of these could be rearranged to be able to take initial velocity out. But another one is a lot of questions start with V1 equal to 0, which is really nice because if V1 is equal to 0, a lot of these terms go away and our formulas become a lot easier. So that is probably why we normally have formulas with an initial velocity in them. So now that we know, let's do a couple problems together and then we'll be done for this lesson. So a ball rolls down a hill with a constant acceleration of 2 meters per second squared down. If the ball starts from rest, what is its velocity after 4 seconds? And then part B, how far did it move? So we're just doing one example here, a relatively straightforward question. Let's start off by always doing what I like to do. Let's write down all the information we've been given. A bit of a formatting error here. That squared should be up there. So that's our first piece of information that we were given, our acceleration. Let's start with that is equal to 2.0 meters per second squared down. And then we've got our initial velocity is equal to, well, it says it starts from rest, right? So it starts from rest, that means that our initial velocity, big old 0. Just like I had talked about on the last page. Pretty common to see. I mean, not always necessary. Obviously, we'll see lots of questions where that doesn't happen, but just make sure that you're keeping an eye out for when that's just kind of hidden in that question there. And then it says that what is its velocity after 4 seconds? So our time is equal to 4.0 seconds. And what is our final velocity? What is its velocity after those 4 seconds? So all it's meant to do now, I mean, especially at the start here, all you got to do is you just pick your kinematic formulas here. You should have 4 of them that you can look at and see. And then, or 3 of them, I guess 3 main ones, and then 4 with that one little iteration we had in the middle, and then pick out which one works best. And in this case, it is our first one. Obviously, we're trying to find V2. We have V1, A, and delta T. So we are going to use V2 equals V1 plus A delta T. And super nice, our V1 is equal to 0. So that cancels out. We can get rid of that right away. So all we are left with is V2 is equal to, now I'm changing to my little step here where I like to do things in scalars. So V2 is equal to positive 2 or negative 2, depending on what you chose. Let's actually do that. Say this was our hill. And it's going down the hill. Well, if it's only going down the hill, it totally makes sense to be able to make a down positive. So down the hill will be positive. We'll make this a positive 2.0 and then multiplied by the time, which is 4.0. And I am making I'm making a bigger deal out of this question than I think it is. I think most of us have probably already realized that the answer is going to be 8.0 and it's positive. So it's 8.0 meters per second. And since we said positive was down, then it is going 8.0 meters per second down the hill. It's going down the hill. And we check our sig figs. Our sig figs in the question are, we've got the exact same amount as we do in our final answer. So there we go. That is our answer. And then how far did it move? So now the next question is asking, what is the displacement? So what is the displacement? Well, we're going to have to use a different formula for this one. I'm thinking we use the one where delta D is equal to all this good stuff here. So let's write that out. We've got delta D is equal to V1 delta T plus 1/2 A delta T squared. Really, really nice. Again, this right here is 0. V1 was 0, so that makes this whole thing, right? V1 times delta T, doesn't matter what delta T is there, that whole thing is going to be equal to 0. So therefore, when we move on, we have got delta D equals 0 plus 1/2 times A, which is positive 2, times delta T, which is 4.0 squared. So we do this and we've got 16 times 2 and then divided by 2. So our answer will be 16 meters is our displacement. We want to have 2 sig figs like we did in the question. So 16 meters down. So that's our final answer. So now it's up to you to go and practice the homework problems on your own. You should have several that you can do on the kinematics equations. When you are doing them, do not forget that if we have an object accelerating due to gravity, that acceleration is always going to be 9.8 meters per second squared down, and that if an object is thrown straight up in the air at the very top of its path, it's going to stop, right? So if you're throwing an object straight up in the air, when it reaches its peak height, it has an accelerator, or it has not an acceleration, my apologies. It has a velocity of 0 before it starts coming back down. Just a very, very brief velocity of 0 when it reaches its peak height. Okay. And the last thing that I would want to mention to you is do not forget to convert your units. This is one of the major areas where students end up getting tripped up on questions and get their answers wrong because they forget to convert units. So do not forget to do that. Okay? Good luck. Let me know if you have any questions, and we'll talk to you soon.